Hi everyone, this is Facundo Molina. I'm a PhD student from University of Rio Cuarto in Argentina, and here I'm going to present EvoSpex, an evolutionary algorithm for learning postconditions. So to start, let me describe a typical automated analysis scenario. Usually, when we want to analyze our programs, we use some program analysis tool that provide us with some feedback on the behavior of our programs. And when we incorporate a specification of the intended behavior, the analysis can be considerably improved, allowing us to catch more bugs or to have better guarantees of the behavior of our programs. But unfortunately, specifications are often unavailable, and this emphasizes the relevance of the Oracle problem, which is the challenge of distinguishing between expected and unexpected software behavior. There are many approaches that one may take to the Oracle problem. One is the use of manual specifications describing the intended behavior of the software. Another one is to try to analyze the software in order to find general software faults, such as unexpected exceptions. And another one is to try to derive specifications from existing software elements, such as previous versions of the software. Our work focuses in this last approach to the Oracle problem, and more precisely in a particular type of oracles called postcondition assertions. The term postcondition dates back to the work of Hoare that introduced this notation to analyze program correctness and defined a postcondition as an assertion that holds after every legal execution of program S. So for example, if we have an implementation of, let's say, an AVL tree, and we also have a routine for insert elements into the tree, a good postcondition assertion for method add should check that the resulting AVL is still a valid AVL, that is, the representation invariant is preserved, that the element that we were trying to insert was effectively inserted into the tree, and that all previous elements in the AVL are still there. So our idea here is to derive a postcondition assertion capturing the method's current behavior. So the current behavior is considered valid, and any other behavior is considered invalid. So in order to derive a postcondition assertion, we should consider all the possible executions of the method, the valid ones and the invalid ones. And among the postconditions that one may consider, we have many. One may be true, that captures all the executions, false, that captures no execution at all, and the one that we expect to have is the one that captures the valid executions while rejecting the invalid executions. So our idea here is to use an evolutionary algorithm that searches for such a postcondition. Essentially, our technique has two phases. One is a generation phase that uses test generation and state mutations in order to produce the valid and invalid executions, and a learning phase that essentially uses an evolutionary algorithm to search for a postcondition that captures the valid executions while rejecting the invalid ones. So the generation phase has as a goal generating valid and invalid method executions. To do so, we take the method under analysis and then use a test generation technique that provides us with a test suite from which we take the valid executions. And more precisely, these executions are represented as state pairs, where the first component represents the state before executing the target method, and the second component represents the state after executing the target method. From there, we use a state mutation technique that allows us to build the invalid executions by mutating the post-states of valid executions. And more precisely, this mutation essentially takes the value of a variable and replaces it by a random value of the corresponding type. Then, in the learning phase, the goal is to produce a postcondition assertion that accepts every valid method execution and rejects every invalid one. So what we did here was to implement a classic genetic algorithm that evolves a population of candidate postconditions by using classical genetic operators such as mutation and crossover that allow us to explore the search space of candidate postconditions until we find the desired postcondition or we met some stop criterion. The search space explored by our algorithm is composed of logical expressions built using a JML-like language. What we do is to use navigation and literals to build expressions denoting primitive types that are then used to build logical expressions involving negation, numeric comparisons, pre- and post-state comparisons. We also use navigation and reachability to build expressions denoting non-primitive types that are then used to create logical expressions involving null checking, pre and post state comparisons, quantification expressions. And also, we combine expressions from these two worlds to build more complex ones, involving cardinality, membership, quantification, and so on. And these are essentially the building blocks of our postconditions. Another important aspect of our algorithm is the fitness function, how we evaluate how good is a candidate postcondition assertion. At a certain point during evolution, a postcondition assertion may accept some valid executions, but not all of them, and may reject some invalid executions, but not all of them. So what we do here is to compute the set of executions that are incorrectly rejected by the assertion and the set of executions that are incorrectly accepted by the assertion. And then we compute the fitness value by using this formula, and the algorithm's goal is to maximize the value of such a formula. And the way of doing so is to minimize the amount of executions that are in the gray area and to maximize this reward that is essentially a fraction related to the assertion length. In order to evaluate our technique, we focused on two research questions. The first one related to the deficiencies of the oracles produced by our technique compared with related tools, and also in the ability of our approach to reproduce manually written contracts. So in the first case, we need to define what are oracle deficiencies. So for a postcondition, an oracle deficiency may be a false positive, that is a program state reachable after executing the method that is correct but the assertion rejects. Or it may be a false negative, that is a reachable program state after executing the method that is incorrect but the assertion accepts. And what we did here was to infer postcondition for 200 methods taken from 16 projects of the SF110 benchmark, and inferred postconditions using our technique and the well-known invariant detector DICON. And then we searched for evidence of false positives or false negatives on the inferred assertions using an oracle assessor called OASIS. And these are the numbers that we found, and essentially the takeaway here is that EvoSpex produces more precise postconditions with fewer assertions compared with DICON, and that the postcondition of both tools still allows false negatives, which suggests that the postconditions can still be improved. Then, in the second experiment, since our technique derives the postconditions from the program behavior, in order to analyze the reproduction of manually written contracts, we needed programs that were correct with respect to a manually provided specification. Thus, we took some classes from a verification context in which the programs had already been proved correct with respect to the specification, and from a synthesis context in which the programs were derived from an abstract specification. Then we used EvoSpex to produce postconditions for these programs and then compare which properties of the original specification were present in the inferred postconditions. And in these cases, our algorithm was able to reproduce a set of rich contracts. For example, the correct addition of elements into an array tree, also the correct counting, addition, or removal of keys and data from a map structure. In the synthesis cases, our technique was able to capture contracts such as the addition, the correct addition of elements into one bag or another, also to assert that a method properly finds the minimum in a bag. And in summary, EvoSpex was able to reproduce 50% of manually written contracts, and for 74% of the analyzed methods, EvoSpex reproduced at least one complex postcondition. So to finish, let me highlight some remarks. The oracle problem is a relevant problem in software engineering. Derived oracles are specifications that can be obtained from existing software elements. Evolutionary algorithm can effectively derive oracles from program behaviors, as evidenced by EvoSpex and other recent work, and that EvoSpex can capture sophisticated and interpretable properties for class implementations. Thank you very much for listening.